Hello and welcome to the GeoDict 2022 workshop for visualization. My name is Steffen Schwichow. I'm a senior graphics designer here at Math2Market, and in this workshop I will show you how to use the visualization features in GeoDict 2022 to create impressive images and animations of your 3D image data, your microstructures, and your simulation results. First, we clarify why visualization is so important that we even dedicated a whole workshop to this topic. Our brain processes visual information faster than text and numbers. We do not have to learn how to see pictures, but we do have to learn how to read. And even if the image does not communicate the core information, it can at least attract attention and make the interested person search the content for the desired information. A good visualization, no matter what kind, should make it easy for the viewer to acquire the desired information quickly and effortlessly. The viewer's expectation of the validity of the image in relation to the content plays an important role in this respect as well. The result of this workshop will not be a fixed setting that can simply be applied to all cases. Every microstructure and every result is different and has to be considered for itself. Rather, we will learn the basic principles and a solid understanding to be able to present our microstructures and results effectively in the future. To achieve this goal, the workshop is divided into 3 parts, each roughly 30 minutes long, with a 10-minute break for questions after each part. In part 1, we will learn how we can visualize 3D image datasets and the associated segmented and voxelated microstructures. We will make sure that we find a good compromise between descriptive and attractive visualization. We will then save our results as image files. In part 2, we will use the knowledge from part 1 to visualize a result field from a simulation and the corresponding microstructure. In addition, we will get to know further visualization options for result fields. We will then save our result using the built-in GeoApp Easy Image. In part 3, we will look at the possibilities of video generation in GeoDict. We will see how to create videos using the result viewer and how to apply and adjust the templates in the video dialog. Now, without further ado, let's dive right into part 1. First, we start GeoDict 2022. You should have received and unpacked the workshop materials files. The first thing we want to do is changing GeoDict's project folder to the workshop files. In GeoDict, we change the project folder by selecting the project folder icon in the toolbar and choosing Select Project Folder. Navigate to the location where we have saved the workshop files, select it, and click Select Folder. All GeoDict generated files will now be stored here in your project folder. We will also find all materials that we need for this workshop here. Next, we will import a 3D image dataset in form of a .raw file with import GeoVol. We open import GeoVol by going to the menu to Import and selecting import GeoVol from the list. Next, we click on Browse down here in the module section. We navigate to the part 1 subfolder of our project folder and then double-click the file, starting with the name Artificial 3D Image Data and a lot of numbers. Based on the formatting of the file name, GeoDict automatically recognizes the values for an X, and Y, and Z, as well as the voxel length here. We only need to enter the value of 512 for the header size, the last number in the file name. Quick tip: if you are not sure which size to enter, leave the field empty and press Image Processing. The following error message suggests a size for the header. With the correct header size entered, we click Image Processing again. Import GeoVol opens, and we can view and edit our 3D image data. If you are interested in importing 3D image data and want to learn more about it, I recommend the Image Processing and Image Analysis workshop by Andreas Grieser. It will be available on YouTube after this user meeting and workshop week. For us, Import Geo has now done its duty. We can close the dialog because what we wanted is that our 3D image data is loaded into GeoDict. We can now, here below, click on Close Dialog. What we see here now is the basic 2D visualization of the 3D image data. Up here, we can slide through the dataset by dragging the slider with the left mouse. We can also use the mouse wheel to do this. And here, we can change the axis from which we want to view our data from by selecting the axis from the drop-down list directly here. Although the 2D mode can be informative and interesting, the 3D mode gives us more visual possibilities to explore our data. To switch to the 3D mode, we use the icon in the toolbar up here. First, we learn how to adjust the position and rotation of our camera in the visualization area to get a better view of our dataset. We rotate the camera by holding down the left mouse button in the visualization area and moving the mouse. We can change the position of the camera by holding down the middle mouse button or the mouse wheel and moving the mouse side to side or up and down. We can zoom by holding down the right mouse button and moving the mouse back and forth. I recommend a camera position that shows 3 sides of our dataset as evenly as possible. If you can already identify an interesting region like this, it should be visible. We can also adjust the position, zoom and rotation in the camera tab of the visualization panel. To do this, select the camera tab and you can influence the position in the translation X and Y fields and the zoom in the Z fields. The rotation can be adjusted in the rotation, heading, attitude and bank fields and also in the X, Y and Z fields. The difference is the rotation system by which the structure rotates. For perfect rotations around the XYZ axis, we will later use the rotation XYZ. To reset the camera settings, you can either use the Reset View button in the camera tab up here, or right-click in the visualization area and select Reset View. We now set up our camera and then proceed to the next step, the visualization of our 3D image dataset. To adjust our 3D image dataset, we select the Volume Field tab in the Visualization panel. Here we find the basic visualization settings for volume fields and 3D image datasets. First, we will have a look at the Color Map dialog that controls the color and transparency settings. To do this, we click on the Edit button at Color Map. The Color Map consists of 3 sections. The first section shows the raw data histogram, which shows us the distribution of the image data values. That allows us to set the minimum and maximum data range of the visualization. Here we can choose between different value ranges: manual, min-max, extended and percentiles. By default, it is set to manual with the minimum and maximum set to the respective min-max values. We set this value to percentiles and accept the automatic values 99 and 1 for better use of the color space in the interesting part of the image data. In the second section, we have the transparency settings, which maps data values to transparency values. Because this is disabled right now, this is grayed out and has no effect at the moment. Finally, we have the color section. Here we can define the colors for the data values. This setting is also reflected in the color scale that we can see here on the right side. Lastly, we have the Load Color Presets button here. Clicking on it opens a dialog of already created presets from which we can choose. To apply one, we select it and click OK. To save a known preset, we can enter a name here and press Save as New Preset. But our goal is to present our 3D image dataset in the usual black and white look, so we select the black to white preset and click OK. We saw that GeoDict automatically applied our changes and updated the view. Because this is going to slow us down in the next step, We disable this feature by unchecking the box next to Apply Immediately. This means that any change we are going to do is not reflected in the visualization area immediately. But once we click Apply, it will be updated. We now want to use the transparency to get a better view into our dataset. Although we can see the different material phases on the domain surface very well, we have no insight into the inside of the dataset. Our goal is to clearly bring out the white and light gray material phases. Try to present those two in a particularly precise way, while still allowing us to take a look inside. For this purpose, we want to define a custom transparency transfer function. To do this, we first activate the transparency section by checking the box here. We can see the material phases represented in the data histogram in the background. From left to right, we have the dark pore space, dark gray grains, lighter gray grains, and finally a cluster of white grains. We can also now manipulate these linear functions by moving the control points and adding new control points to the function. We click on the free area between 2 points. On the right side, the button Add Point will be activated and we can add another point. We can also right-click in the free space between 2 points to add a point like this. The new point is automatically selected, which can be seen by the smaller white rectangle inside a black rectangle. On the right side, we can also see the position and the opacity value of the point. First, we add 2 more points, here and here. The exact position doesn't matter. We will position them together in the next step. The position of the first and last point is fixed. For these, we can only adjust the opacity value. For the first point, here, we use an opacity value of 0.2. We can either enter the values of the point directly into the opacity field or manipulate the point with the mouse. To do this, we click on the point and hold down the left mouse button. Then we can change the value of the point by moving the mouse up and down. If we move the mouse left and right, we can also change the position at the same time. The direct input is recommended if you want to work precisely. For the next point, the second point, we set the opacity to 0.2 and the position to 12. For the next point, the third point, we set the opacity to 0.7 and the position to 16. For the next point, the fourth point, we set the opacity also to 0.7 and the position to 20. For the next point, the fifth point, we set the opacity to 0.9 and the position to 27. And for the last point, we set the opacity also to 0.9. We take a look at the intermediate result with a click on Apply. We can identify our 2 types of grains very well, but there's still some contrast missing. We go back to the Color Map dialog and add the same number of points in the color section by right-clicking in the free space in the color section, down here, and selecting Add Point. We do this till we have added our 4 additional points. We also adjust their position to match them roughly to the position in the transparency section above, again by dragging them with the left mouse button. When we are done with this, we can press Apply again. So far, nothing has improved. For the final touch, we adjust the color values of the control points. The first and last point are already set correctly. For the second point, we choose the same color as the first point, black. To do this, we either select the respective point first and then click on the button Point Color, or we use the right-click dialog of the control point and select Change Color. In the color dialog, we select the respective color, black in this case, and press OK. The gradient between the points is now a constant black. That means that all values that are representing our 3D image data in the data range are colored black. For the two middle points, third and fourth, we set the color to a medium gray, again via the right-click dialog or by selecting the point and using the color dialog button. Since there's no middle gray in the color presets, here we can simply start with white by choosing it here and then adjusting the brightness of the color here till we have a gray with the value of roughly around 127. We apply this color and we do this also now for the fourth point. For the fifth point we choose the same color as the last point, which is a pure white. We can simply select one here. As soon as we are done, we click Apply to see the result. If we navigate around our image data, we can see the distribution of the middle grains very well, and we can also evaluate the extent of the clustered grains here. Before we go on, we want to save the current state of our work. We have a look at the lower left corner of the color map dialog at these 5 buttons here. In every GeoDict dialog, the settings can be saved and reloaded. To save the settings in the color map, we click on the Save Current Settings to File icon in the lower left corner of the dialog. A file dialog opens. We can name our settings file to our liking. I will use color map 001 and save it with a click on Save. Depending on the dataset, design specifications by the corporate design, or simply because of personal taste, a dark background may be desired. To do this, we first close the color map dialog and click on the icon for color and visibility settings in the toolbar up here. In the color and visibility settings dialog, we click on the button next to the background color, which is white at the moment, and we click on the 3 dots. For a dark background, I recommend not to use a black, but a very dark gray. This is more comfortable for the eyes. From experience, I recommend a value of around 40 or even 60 for the RGB values. Again, by direct input or by dragging. The color change will apply immediately, and we can close the color and visibility settings by clicking here on the X or here in the bar. As we can see as we move around, this kind of visualization is also very pleasant, and everything is still well visible. We now want to save these settings together with the color map settings. Before, we only saved the entries in a specific dialog, the color map dialog. Now we want to save all settings corresponding to the visualization. We can do this in the visualization settings here on the right side in GeoDict. We open it by clicking on the button here. All settings for the visualization of microstructures, volume fields and so on are accessible through these settings here. We will have a closer look at the possibilities of the visualization settings later in the workshop. For now, we only look at the save and load function. The icons for saving and loading are the same as in other GeoDict dialogs. We click on the icon for saving the settings here, give our file a name. I use view status 001 and save it. That also allows us to experiment a bit with the colors without losing our current progress and reuse it for other similar datasets. With our settings saved, we open the color map dialog again and going to try out some other colors for our dataset. We uncheck Apply immediately first again. In the color section of the color map, we look for points 5 and 6, the color points for the clustered grains in white, and changed the color. Here you can now experiment a little bit or follow me in the choice of colors. For the grains in white, we choose a strong but light orange this here for both points. Here and for this point also. For the medium gray grains, we choose a medium light blue 4.3. Here, this one, and this one. 4.4, we choose a strong purple. This one here. And click OK. This creates a light, pleasant shade. To see our change, we click on Apply and wait a second for the update in the visualization area. Our dataset now has a pleasant complementary contrast and colors that harmonize with either light or dark backgrounds. We close the color map and save our visualization settings under a new name. Maybe call it View Status, Orange and Blue, and click Save. Since we are about to switch to voxel visualization, we want to conclude the basic volume field visualization by finally saving our work as an image. For this, we position the camera in a comfortable angle and position. Maybe like this here. Then we either navigate to the menu File, Save Image As, or use the icon Save Image As here in the toolbar. Here we have several options now. First and foremost is the resolution. If we keep this at current resolution, it will keep the visualization area resolution as is. And we can also define a totally custom resolution here. There's also the option of selecting from a variety of presets, which are predefined standard resolutions or standard video resolutions. For now, we will keep this at current resolution. Next is the option to crop all empty space. That means that we let GeoDict automatically remove the empty background space in the image. Thereby, we do not have to go through an image processing software in order to cut the image. But of course, this also changes the resolution of the final image. The image is cropped to the next picture element, in this case to the material legend, the volume field legend, the GeoDict logo and the axis cross. Without these legend elements, the domain borders of our dataset would be the next picture element. If we still want to have some space around the center of the image, despite the automatic cropping, we can choose Embed after cropping. For all sides around the image, we can define the free space individually. We can choose between an absolute value in pixels or a relative value in percent. For now, we do not want to embed space. Finally, we can choose whether we want to save the image with a transparent background or not. I would recommend to save images with a transparent background. This gives us the freedom to choose another background color later and to seamlessly integrate the image in a PowerPoint presentation, for example. For now, we uncheck it to save the image with our defined background in gray, and we also uncheck Crop All Empty Space to get the image in the original size. We'll take a closer look at the other options later in the workshop. If we are done, we press OK, give our image a name again, and press Save. Now we can view our image by opening our GeoDict project folder. The fastest way is to click on the project folder icon and select Open Project Folder. As we can see, it was saved as expected. We do not have our image cropped and we also have an opaque background. We will take a closer look at how we can clean up our image later in the workshop. We close the image and go back to GeoDict. Now that we have seen how to visualize gray value image fields, we are going to look at how to visualize segmented microstructures. The difference is that in the gray value fields, we have a continuous value domain, while in the segmented microstructure, we have a small set of discrete materials with each voxel being assigned to one of the materials. Let's get started by getting rid of our dataset by clicking on File, Discard Structure and Fields. Now we load our segmented microstructure. This corresponds to our example 3D image dataset and is already prepared as a GeoDict file in the workshop's materials. To load it, we either navigate via the menu, File, Open Structure, or click on the icon, Open Structure in the toolbar. We navigate to the subfolder Part 1, select the segmented crane example GDT, and click Open. From the material legend, we see here that different material phases have been segmented and given their own material ID. The small grains were assigned to material ID 1, the middle grains to material ID 2, and the clustered grains to material ID 5. The pore space was assigned to the material ID 0. The material ID colors we see here are the standard colors in GeoDict. These were chosen to create the highest possible contrast between the materials. First, we will adjust the material colors. We will proceed according to the same principles as with our dataset in order to direct the viewer's attention to the area of interest. To change the colors, we will open the color and visibility settings again. First, we set the background color back to white. Down here, click on the button and select white from the presets. Next, for material ID 1, the small grains, we click on the color button, currently red, and select white. This produces the least contrast against the white background, since we do not want to attract the viewer's attention to the small grains. For material ID 2, the medium grains, we click on the color button, currently green, and select a dark gray. This is a solid contrast against the white of the small grains. Next, we define the highlight color for the clustered grains with the material ID 5, that are currently purple. To comply with the corporate design guide here at Math2Market, I will choose our corporate color red. Last thing to notice, for each of the material IDs, we can actually make them visible or invisible. But for this example now, we keep it as it was, with all materials visible and the pore space invisible. We close the color and visibility dialog. Now we notice that the material phase of interest, the clustered grains here, to which we would like to direct the viewer's attention, is in the shades right now. To change this, we will move the light source. We click on the icon for the light source in the toolbar here, and now the function of the mouse in the visualization area has changed to moving the light source instead of adjusting the camera. Also, a small icon in the visualization area has appeared that shows us the position and direction of the light source. We move the light source by holding down the left mouse button and moving the mouse. We make sure that all sides are still clearly visible despite shadows, and that the shadow on the side here, the previously illuminated side, does not become too dark. So we adjust it roughly like this, and as soon as we are satisfied with the result, we switch back to the mouse mode with the toolbar icon here. And now we again can adjust the camera with the mouse. Next, we will change the render style of our microstructure. We change to the Structure tab up here and have a look at the Structure mode. Currently, the selected render mode is Box. This renders the microstructure in the actual voxels. We choose Smooth, which creates a surface mesh from the voxels and displays it. This takes some seconds and depends on the amount of different material IDs that are in the structure, how much time and memory it takes. But therefore we get a very nice surface visualization with gloss effects that support the perception of the surface topology. We also have a GPU-based renderer that displays the microstructure as voxels. It is much faster than the box renderer and the smooth renderer if you have a good graphics card. The limit here is the available graphics card memory into which the microstructure must fit with its resolution. Furthermore, not all visualization features are currently available in the GPU renderer. For our image, we are going to use the smooth renderer, so we switch back to it. Finally, we add some visualization effects that make it easier to see the topology and the depth of our microstructure. For this, we switch to the Camera tab. There we activate Show Outlines, Show Halos, and Global Lighting. The global lighting takes some seconds to compute. All effects require some performance and can cause rendering time to increase in the visualization area, especially for large structures. As we can see, the pore space around the cranes is now more visible and easier to identify. We will see better examples later where this effect works even better. Next, we want to save an image again, but this time we want to clean up the visualization area first. For this image, we want to remove the material legend over here and the access crossdown here. The GeoDict logo here cannot be deactivated in the workshop license, so we have to leave it in for now. We can do this either via the menu under View, Legends and Overlays, and remove the checkmark from Access and Material Legends. Or we can use the visualization settings by clicking on the button up here on Detailed Settings. The visualization settings will automatically open in the right place, and we can clean up our visualization area there. Now that we have prepared our visualization area, we adjust our camera and open the Save Image dialog up here again. This time for a change, we select the full HD preset right here and save it with automatic cropping. We are also going to embed after cropping. We are going to embed a 5% white border all around the image. We keep the transparent background disabled for now to actually see how GeoDict is cropping the image. We click OK and give our picture a good name. Now we go to the project folder and open the image. As we can see, the image was properly saved with an embedded border all around, which roughly is the 5% we put in. We go back to GeoDict and now we can save our visualization settings so that we can reuse them later. And this completes the first part of our visualization workshop. We have visualized a 3D image dataset and a segmented microstructure. Thereby, we got to know some visualization principles and some tricks in GeoDict. We also saved our results as images. We leave GeoDict open and return here after the questions and the break.